In this video, I would like to talk about applications of exponential functions. There are so many interesting ones. These are just some among them. Population growth, decay, radioactive decay, this is more chemistry, interest, which is actually mortgage, comes into exponential growth as well, and Newton's cooling law, which is pretty interesting with, let's say, respect to cooling of a pizza pan, but it can have an interesting forensics applications as well, such as figuring out the time of death of a cooling body if the body is discovered within 24 hours. So it has some interesting applications as well. So these are just some of them. Some of them sort of follow this standard model that we will talk about. In fact, a lot of them do, like population growth, decay. You can write it as an exponential, or radioactive decay, or interest. A lot of them fall into this category. The only one that's sort of an exception is Newton's cooling law. And of course, there are applications such as mortgage that do not use E as the base. They may use some other bases, and sometimes once in a while you see that in biology as well. But let's take a look at the standard model at first, and then we'll take a look at some other applications. And then there are also logarithmic applications, which we may take a look at section 3.5 for some of the log ones, the really interesting ones such as earthquake, the Richter scale, or some other ones like with the sound of music and decimals, that both of them use logs essentially. But let's start with exponential models. So this is for section 3.2 and 3.3. They're kind of dispersed throughout, and maybe even some 3.1 as well. So A0, that's basically the initial amount, whether it's money, population, whatever it happens to be. K is usually the growth or decay rate. It could be written as a decimal or as a percentage, which means you have to convert it to the decimal. If it's greater than 0, generally we have growth. If it's less than 0, we have decay. And T is time, which could be really years, but it could really be minutes. It could be anything as far as time is concerned. And A of T is amount at time T. So if all the variables are given, then we can simply plug them into the model and solve. But sometimes the rate is not given and we have to solve for it. And that's generally a couple of situations that arise. Let's take a look at population growth first. So in population growth, the population in Canada was 31.3 million in 2000 and 33.4 million in 2007. Determine the time from 2000 until Canada's population doubles. So 2000 is basically like T equals 0. Okay, so A0 is our initial amount, is 31.3. Now we do need to find K. That's why we're given the time and the amount, the second time and the amount, to be able to find the K. So this is how we set this up. 33.4 equals to 31.3 times e to the k times 7. And then I generally try not to round. In fact, sometimes I put it all in the calculator. Here I rounded just to show you guys. But the more decimals you have here, the better, because you don't want to round too early. You can actually leave it as 33.4 divided by 31.3, or use the answer key in your calculators. But then, okay, so once you divide, you can take a ln of both sides. If you recall from the previous section, we said the ln and the e cancel each other because they're inverse functions. In fact, we use this property a lot here. So we just end up with 7 times k equals to a ln of this, because the ln and the e canceled. And you can just divide by 7, and we'll get k approximately. Again, have as many decimals as you can because you don't want to round. And this is what I have. Okay, it's positive, so we do have growth. Now, when would it double? Well, we'll literally double the initial amount, which is 62.6. Sometimes when it doubles, you don't even need the initial amount. You can write it as 2A0 or 3A0 if it triples, and so on. So, but here we do have it, so we did use it. Notice how we divide by the initial amount, so we get 2, which makes sense when you double it, equals to e to that k times t. And then we take a ln of both sides. On the other side, it cancels. So we get the ln of 2 equals to just the exponent. and then we divide by that k, and so we get about 74.72. So round it to as many decimal places as that makes sense. With the years or time, about 2 decimal places is usually okay. So it would take about almost 75 years for the population in Canada to double. So it's not a very fast growth, but still, it's pretty good actually. Okay, the next one I'd like to take a look at, there is actually one, I think, or a couple maybe in section 3.2, I believe, is Newton's cooling law. Again, as I mentioned, could be interesting in forensics or other situations. And so we have this equation that we want to use. So you may want to write this down as you're working on the problems. So that's a temperature. Let's take a look at how we describe everything. So A is basically temperature of the medium, or maybe the air or the surroundings. Let's say if you start, it's usually the final room that you end up with. Final room or the surroundings or whatever you end up, the object ends up. T0 is the initial temperature of the object. Let's say if it was in the oven, so it would be the temperature of the oven. K is the rate of cooling. You could really use it with warming as well, so it could be positive or negative. And T is the time, which again could be in minutes, usually is. And T of T is the temperature of the object at time T. So if it's cooling, it should be less than the original. So here we have a problem. A thermometer is taken from a room at 75 degrees Fahrenheit to the outdoors where the temperature is 20 degrees. The reading of the thermometer is 50 degrees Fahrenheit after 1 minute. So that again tells you we have to find the rate of cooling. So the key is, and then you have to find the temperature we're given different time periods. I think we have to start with 1 minute. So first find K. Okay, and I try to set this up here. So T0 is 75 degrees, A is 20 degrees, and we have to find the K, but we do know that T of 1 equals to 50 when T equals to 1. So we have, this is how we set this up to find the K. 50 equals to 20 plus 75 minus 20, e to the K times 1. And here typically you follow the order of operations. Usually you would need to work out what's in parentheses here. So that would be 20 plus 55 e to the, it's just K because it's K times 1. Then you can subtract 20 from both sides, basically trying to isolate the exponential. So we'll have 30 equals to 55 e to the K. Then we divide by 55. So I get this repeating decimal. So again, I try to write as many as I can, or use the answer key on the calculator, equals e to the K. Then we can take a ln of both sides. So K is a ln of this decimal, which you can leave it like this if you prefer to be more exact, or find the decimal for it. So I think I did find the decimal. Again, if you write this many decimal places, how many do I have here? About 7. Then it's usually pretty close to the actual answer. Or you can use the answer key. See how I'm kind of trying to explain it. So that's second and the little negative on your calculator. It's pretty handy. So I put it back in the original equation. And now we can plug in the different little t values to be able to figure out 1 minute, 5 minutes. I think we're trying to figure out, I thought it said after 1 minute, but maybe we had after 1 minute was given to find the K, and then we'll have to find 5 minutes. We're just going to go with a problem. You can see it in your homework as well. So it probably was a typo too. So we can plug in 5, and notice how we'll get approximately 22.66 degrees. So 5 minutes, it's already pretty close to 20 degrees. And notice 10 minutes is even closer. So I put it in a calculator. So it's a little bit easier when you're just plugging in the time. If you had to solve for the time, then of course you would need to use logarithms, maybe a little bit more challenging. How long will it take for the reading to drop to 22 degrees? Well, here's where we solve for the time. Notice how you can put in the 22, basically like working with the equation. Subtract 20 from both sides, you'll get 2. Divide by 55. So again, you'll get a long decimal, and then I just did a ln of the answer equals to the exponent. So then you can just divide by the rate. And so I got about 5.5 minutes. So that's how you would solve for the time. Okay. Then we have a radioactive decay example. So again, that would use more of the standard model. Let's say iodine 131, a radioactive substance that is effective in locating brain tumors, which is good in medicine, has a half-life of only 8 days. So radioactive materials do have half-life. A hospital purchased 20 grams of the substance but had to wait for 5 days to use it. How much of iodine was left after 5 days? So hopefully you can figure out, well, 8 days you would be left with exactly half. Now, 5 days is a little bit shorter, so you should have a little bit more than half, so a little bit more than 10 grams. That's how you can approximate your final answer when you're working on these. But let's use the standard model. So first we use the half-life to figure out the K, or the rate of decay, which is what I did. So I used 10 for the half, equals to 20 e to the K times 8. So divide by 20, we get a half equals to e to the 8K. Take a ln of both sides. So I got K to be about negative 0.0866 and so on. And it does make sense for it to be negative because it's decay situation. How much is left after 5 days? Now that we have the K, we can plug in the 5 and we get, it does correspond to what we suspected, about 12.969 grams. It's a little bit more than 10, which is good. Okay, once in a while we have percentages that are given to us, and we have to calculate the half-life. So here is tritium is used in nuclear weapons to increase their power. It decays at the rate of 5.5% per year. Calculate the half-life of tritium. You have to be careful with the decay. You cannot just use the percentage stuff, how sometimes you can do it with the growth. What I would do to set this up, because 5.5 decays, with the decay, figure out how much is left of the material. Well, it would be 94.5% left after 1 year, and then use it to find the K. So focus on how much is left, not how much decays. So, because we don't know the initial amount, occasionally that happens, then we usually have the information if it doubles or triples, or we have a half, or in this case we have 94.5%, or make it a decimal, 0.945 times A0. And notice, because you have A0 on both sides of the equation, so this is the final amount, this is the initial, you can divide by A0 and it cancels out. So you just end up with a decimal, 0.945 equals to e to the K. Then take a ln of both sides and that would be your K. Again, I just kept it as the ln to avoid the rounding, so you can put it right there in the exponent. And to figure out the half-life, I put a half of A0. Again, we can divide by A0. Again, so it doesn't matter how much it was initially, we can still figure this out. Then take a ln of both sides. And so a ln of 1/2, and then a ln and the e cancel, so you just end up with a ln of 0.945 t. Then you just divide out. Be careful, do not cancel the ln's. You still have them there. Put it in the calculator exactly as is. So we'll get about 12.25 years. So this one doesn't last as long as some of the materials, like carbon dating, that can last for thousands of years. And here lastly we have the interest for the compounding continuously, which you probably have seen already. So I'll very quickly just go over it. It's A equals to P e to the RT, sort of looks like PERT. So if $1,000 is deposited in the bank at 10% compounded continuously, how many years will it take for the money to grow to 3,500? Well, we can set it up like this. 3,500 equals to 1,000 e to the 0.10 t. Simplify it, divide by 1,000, we get 3.5 equals to e to the 0.1 t. Then a ln of 3.5 equals to 0.1 t. And then c is equal to a ln of 3.5 divided by 0.1, which is about 12.53 years. So quite a few years, but still pretty good. And that's it for this section.